All right, ladies and gentlemen, this is the first video for our simple harmonic motion unit. This is going to cover both springs and pendulums are going to be sort of the two big ideas and topics for this unit. But we are going to start with springs, and most people have seen a spring before, but we want to start with this little video. We took this during class using an app that actually tracks the object. We've got a little bob on this spring, and it's actually going to track it as it moves up and down. And notice that this pattern sort of repeats itself. I know it's moving left and right, but ultimately, if we go back here a little bit, we can see that the bob moves up and back down, and up and back down, and up and back down, and keeps repeating that process. And the iPad took some data. These are not graphs we're super interested in. They don't tell us much, but this one, this Y position. So it's mapping where our object was versus what time it was. And notice that this just keeps repeating itself. This pattern repeats itself over and over again to relatively the same height in about the same amount of time. This is what we call periodic motion. And we're going to get more specific about it as we go. But for now, it is just considered periodic motion. We're going to start there. And that's just motion that is repeated over equal intervals of time. This mass on a spring is periodic motion. So is the orbit of planets. The fact that the Earth takes 365 days a year to orbit the Earth, it goes through the same motion or repeating motion. We keep orbiting the sun, and it takes about the same amount of time every single year. That's why we use it as a year. Our mass on the spring, if we had video of Zach pulling on it before, just that mass hanging by itself, we would have seen that there's a sort of a natural place that mass wants to be, and that's called the equilibrium position. It's where it feels at rest. It's where the net force acting on that object is zero. The force that the spring is applying upward is the exact same as the force of gravity being applied downward. We call that position x equals 0, or x equals, oh, my projector just went, or x naught. So both of those are proper nomenclatures for that, but it is the equilibrium position. It's the position that it sort of likes to be in. After that, we also have displacement. This is at any point in that video, we had various different positions that object was in. It was, at what it was calling the 500th pixel on the iPad, and then it was back down here. Each one of those different displacements is just a different distance from that equilibrium. That's where we measure from for this stuff. We measure it from that equilibrium position, and we have to include direction. If it goes up from that equilibrium, we call it positive, and if it goes down from that equilibrium, we call it negative. Notice, though, on this graph that we relatively have the same height or depth, and we lost a little bit here and here, but if everything was perfect, if all of our equipment was absolutely perfect, we were in a vacuum, there was no friction, it would just continue at the same height forever. And at this height from the equilibrium position is called the amplitude. It's the maximum distance that our object can get to. And on both sides, both above and below, that amplitude is the same, just in opposite direction. So the height, or the sort of distance from equilibrium up, is the same as the distance down from equilibrium that it can get to at its maximum. We represent that with a capital letter A. A cycle is what we consider a to and fro motion. So this would be here, up, down, and back to the equilibrium position. Or we could say that it is from the peak to the peak. Or we could say that it is from a trough to a trough. In order to complete a cycle, you have to go through the entire motion. You can't leave any pieces off. And you have to get back to the exact same place that you started from. So it is got to include the entire motion. We can't leave any chunks off. And then we have to get back to the same place so that if we continued, we would repeat that motion and repeat that motion and repeat that motion over and over again. The time it takes to complete one cycle is called a period. So if we go from trough to trough, that's like 1.1-ish seconds. But if we tried from here to here, it's about 1.1 seconds also. And over here, about 1.1 seconds. That's a good sign for this experiment. Our period for each one of those cycles should be the same. Frequency is just the inverse of period. It's how many cycles per second, and we just take 1 over the frequency to get the period, or 1 over the period to get the frequency. And we said that these springs move in a periodic motion, but more specifically, and we're more worried about, is this simple harmonic motion piece of it. The fact that these two requirements are satisfied by a spring. We have a restoring force. If you've ever pulled on a spring, you know that it tries to snap itself back to that original equilibrium position. Or if you try to compress a spring, it will go and shoot itself back to that equilibrium. For instance, if you've got a mechanical pencil and you want to take that that little spring that's inside out, or a pen even, some of the ballpoint like clicker pens have them. If you take that out and you try to press on it, it will try to press back against you. That is what's called a restoring force. It pushes whatever is hanging against it or whatever is applying a force back to the equilibrium position. And secondly, that restoring force has to be proportional to how much it's been stretched from that equilibrium position. The farther you try to stretch a spring, the larger the force trying to restore it is. If you take a slinky and you stretch it out, at first it's pretty easy, but as you get farther and farther and farther and farther out, it gets harder and harder and harder to keep stretching that object. The restoring force becomes larger and larger and larger, and that's what's called Hooke's law, and we'll see that in the second half of this video. But ultimately, a system that meets those requirements undergoes simple harmonic motion and is known as a simple harmonic oscillator, or a SHO, S-H-O. And its motion can be modeled as a sine function, which we saw here. These are sine waves from your math classes. These are sines or cosines. They follow these sort of trigonometric lines, which are really, really nice, those curves. So there are a couple pieces of those graphs that I want to label out. A lot of times, and graphing is going to be a major component of this unit. We're going to have to be able to identify different places on these graphs. So the first one is amplitude. And so I'm just going to kind of draw it out here, and it's right here. This line is our amplitude. It is the distance from the equilibrium position, that 0, all the way up to its highest point. That is the same length, the same distance as it is from the equilibrium to the lowest point. So that is our amplitude. The period, again, is the distance from peak to peak, or from trough to trough, or from equilibrium position to second equilibrium position after that. So that entire piece is our period right here. The biggest mistake that people will likely make on this is to say that the period cuts off right there. The problem with that is it didn't go through its full motion. It didn't go down and then back up. It only went down and back to the equilibrium. We need to go down and then above the equilibrium to get to its full period. That's a lot of extra stuff. The second thing we want to be able to do, and that's a little messy, so I'll go back here. Let's see how I can shake this out. Let me erase some of this real quick. What I want to do is actually break my graph into 4 sections. We want to break one period, one cycle, into 4 different sections. Let me get all this erased real quick. And I've done that up here on the left. So I just drew one cycle of a sine wave. I did it twice. There's different ways that can be. But we want to divide it into 4 sections. We'll always divide into 4 sections. And anytime we either have a peak, an equilibrium position, or a trough, I drop a little dashed line from it. And now I've divided it into these 4 sections so that, let's say a problem said that I had a period, remember we represent that with a capital T, of let's say 12 seconds. Period of 12 seconds. And it gave me some time that this object has been oscillating for. Let's say that it was, I don't know, 63 seconds. So this object has been going on for 63 seconds. And the question is, where along this path, sort of where along here, is the object at that 63-second mark? And to answer that, it's really not that troublesome. What we're going to do is we're going to take the time elapsed divided by the period. That gives us the number of cycles that have been completed. So for instance, for this one, if I do 63 divided by 12, I believe that comes out to be 5 1/4. So I've got 5.25 cycles completed. What that means is that my object went through, up, down, back to equilibrium once, and then it did it again, and again, and again, and again, 5 whole times. 5 whole times, but then it also went 1/4 of the way again. So I go up to this first break. So at this exact time, at this 63-second mark, my object is up at the top. It's at A. It's at the amplitude. That's its position. So if we break this down, whenever you do this, whenever you take those divisions, it doesn't matter what this whole number is. That whole number doesn't matter at all. What matters is this decimal. For all the purposes we'll have, it will either come out to be 0.25, 0.5, or 0.75, or there won't be a decimal. Here at the beginning or at the very end, that's where we've got no decimal. If it just came out to a whole number, 5, 7, 113, it would be at these positions. It would be at equilibrium. It would be at 0 for its position. But we can break this up into quarters, 0.25, 0.5, and 0.75. So if I had gotten 0.75 at the end, that means that I went through 3/4 of a cycle and ended up down here at -A. If my number had come out as a 0.5, I would be at my equilibrium position for this graph. I would highly recommend you actually draw out the pictures. A lot of the times they will say something like it starts from the highest position and then goes through simple harmonic motion. That's what your graph should look like, and that will come out with different positions than this graph did. Because now at the half, I'm at -A. Whereas here, my half was the equilibrium. So be sure to draw out those little pictures. That makes it much easier. Another thing about this is the time that it takes to go through, and I'll just draw it down here since I got some space. The time it takes to go through each one of these quarters is the same. So let's say that this quarter took 0.2 seconds. Let's say I was given that by the problem. That means that this quarter also takes 0.2 seconds, and this quarter also takes 0.2 seconds, and this quarter also takes 0.2 seconds. So ultimately it would be 0.8 seconds to get through one entire period of motion. And finally, in any oscillating spring, one period of motion, so I'll put just T instead of writing all the words out. So the period, in one period, we go a distance of 4 times the amplitude. Whatever the amplitude is, we go through 4 of them. I'll sort of label it out here. In this first chunk, we go a distance of A. We go from A to 0 to get to that equilibrium. So we've got a distance of A here. Then down beneath, we go another distance of A from 0 to -A. Then we go from A to 0, which is a distance of A, and back up to A again in the third one. So it is 4A, no matter what. One period has a distance of 4A. Couple of those. This graph points out a couple of different special places within a simple harmonic oscillator, particularly in a spring. When we graph the position versus time graph, so I've got my Y position, my height versus my time, and I've got 0, this is my amplitude, and this is my negative amplitude. What I've got first off is certain velocities. We said way back in the first unit that velocity is the slope of a position time graph. So places like here at the peaks and at the troughs have a slope of 0. They are flat down there at the bottom, which means that their velocity is 0. That makes sense. If you take a look at a spring, an object moving on a spring, when it gets to that bottom point, it stops for just a second before it changes direction. The same is true for the top position. So both of those are our velocities where they equal 0. So at peaks and troughs, velocity equals 0. At the equilibrium position is actually where we have our maximum velocity. Our object moves fastest when it is in its equilibrium position. So if I get it started, as it crosses that middle, that's when it moves the fastest. It's the maximum velocity in the negative direction if it's moving downward. And if it's in the positive direction, if it's moving upward, that it's its maximum velocity in the positive direction. Those slopes are the steepest at that exact point. Our acceleration is actually the exact opposite. We said that as we pull on that spring, the force gets bigger and bigger and bigger. So the farther out our distance is, the closer we are to the amplitude, the more force we have acting, which means that our acceleration is also the biggest, because net force equals ma. If we get a bigger net force, bigger force from that spring, our acceleration's got to be bigger as well. So our acceleration is maximum in the positive direction down here at this trough, and our acceleration is maximum in the negative direction at that peak. In the very middle, at the equilibrium position, our acceleration is 0. We said that if that object is just hanging in equilibrium, it is not accelerating, which means that it has no net force, and at equilibrium, the acceleration is 0 for just a split second as it actually moves. A couple little sample problems, you can check those out on line. But today and in the second day, we talked about Hooke's law. We wanted to give actual numbers to those forces and acceleration. So Hooke's law for simple harmonic oscillators, it has to follow. Hooke's law has to be true and present if you have a simple harmonic oscillator. So it's Hooke's law states that the force is exerted on the object is proportional to and in the opposite direction of the displacement. We talked about this briefly, but now we're putting some math to it. So this force is the force that the spring actually acts with. The force that the spring is applying to our mass, to whatever is hanging by that spring. That is equal to a spring constant with units newtons per meter. And that spring constant is different for different springs. There's no way of just looking at a spring and saying, oh, its spring constant is 100 newtons per meter or 50 newtons per meter. You actually have to do an experiment, and we did one in class to measure that. You can actually find the slope of a particular set of data points, which many of us found in class. So it's that spring constant times how far away from the equilibrium position is, that x, that displacement. And with that, that's like the slinky we were talking about. As we extended farther and farther, we pull the slinky apart, the force that is being applied to our hands increases as well. Personally, I like to write this equation a little bit differently. I like to write it as the absolute value of the force is equal to k times the absolute value of x. This just gets rid of the negative. The negative is only there to say that if I pull to the left, the spring pulls to the right. If I pull down, the spring pulls up. That's all the negative says, and a lot of people get hung up on it. So I prefer to set it up this way. I think it's easier. That gives you the magnitude of the force, and then it's your job to interpret the direction. So that's the magnitude of the force. And a quick example with this, let's say that we had, and this is as hard as the example could possibly get. Let's say that we had some spring, and from it was hanging a 2 kilogram mass. And when we hung that mass on it, the equilibrium position was up here, but now we've stretched it a distance of 2 meters. By hanging that 2 kilogram mass on it, the spring was stretched by 2 meters from the equilibrium position. So we're going to start out with our spring force equals kx. And my question is, what is my spring constant? That's really what I'm looking for. I want to know how stiff this spring is. The stiffer a spring is, the larger the spring force is. So I know my distance. I know that my displacement was 2 meters. That's nice. I like to use meters in my equation. But finding the actual spring force is a little tougher. I've got this mass, but that's not necessarily how much force my spring is applying. But what I do know is that this object is at rest. This 2 kilogram mass is not bouncing up and down. It is just at rest. It's hanging there. If we have an object at rest, that means its acceleration has to be 0. And if its acceleration is 0, that means that the net force is also 0. So we need to decide what forces are actually acting on our block at this very moment. And we've got two. One is the spring force upward. Remember, we extended it down, so the spring force has to point upward. And we've also got the force of gravity, or weight, which is mg of this 2 kilogram mass. So m times g, 2 times 10, is 20 newtons. And we don't know what the spring force is, but we know that the sum of those two forces has got to equal 0. So my spring force I'm going to make positive, and my weight I'm going to make negative, which means that my force of the spring has to be 20 newtons. So if I plug that in, back up here, I just divide 20 by 2, and that gets me a K of 10 newtons per meter. A lot of the problems will give you just two of these pieces of information and tell you to solve for the last one, but this is also a common way of getting there as well, giving you a mass and asking you to find the spring force so that you realize that the net force is 0, which means that the spring force has to equal the weight, but not the mass of our object. And that takes us through the first 2 days of our simple harmonic motion. Through this point, you should have worksheets 1 and 2 taken care of. On Monday, we're going to start in back with energy. We talked about energy with potential energy due to gravity. Turns out that springs also have some potential energy properties, and they can work a lot in the same way. So it'll be a little refresher, but slightly different. Not too bad, though. And we will see you all then.